Hello, Mr. Long. This is FRQ number 1. So part A is the free body diagram for M1. So we already know that there's going to be a T1 because in the diagram T1 is pointing towards the center. But also this, sorry, I forgot to label this M1. This M1 is also being connected by a string. And that string, according to the diagram shown, is T2. That's the other string. So it's safe to assume that T2 would also point this way. And yeah, that's part A. There's two tensions on it because there's one tension pointing towards the center and there's a string attached to this M1 too. And for part B, obviously there's only one tension there, which is the string on M2. There's only one tension on there, unlike M1. So T2 will be pointing like that because there is one tension acting, towards the center for M2. This is the tension acting towards the center. So that's part A and B done. That's the free body diagram. To calculate the period, we can use our the tangential speed formula that we got. So we're going to do V of 2. And the reason why I did V2 is because we're calculating M2. So I would like to mention that, yeah, just so that our units, it's easier to understand. Yeah, we're calculating M2. So for the period. So V2 equals 2 pi R2 because we're calculating M2's period is to T. We can manipulate this formula by, getting T alone with 2 equals 2 pi R to 2 over V to the 2. That's not a square, that's just V2. And so now we can just plug and chug. Our period would equal 2 pi. R2 in the problem is 0.75 meters. And our velocity according to M2 is 4 meters over seconds. And that will give equals to around 1.78 seconds. And it's seconds because these meters would cancel out. So for part D, it's just asking to calculate the tangential speed for M1. We already had the tangential speed formula, but instead of V2, we're going to do V1 because it's the tangential speed for M1, not M2. So we would do V1 equals same one, but instead of R2, we do R1 because tangential speed for M1, not M2. And tension. Or not tension, sorry, period. So we can use the period that we found on the last problem, which is 1.78 seconds. So let's do that. 1.78 seconds. 2 pi. R1 in this problem is 0.4 meters. And that should give you a pre-calculated a value of 2.13 meters over seconds. And this doesn't need direction because we're calculating the tangential speed, and that's a scalar. So for part E, it's asking the y expression for the centrifugal acceleration, aka AC or whatever. Yeah, okay, let's do part E. Part E, we could start using Newton's second law. So right, M equals MA. But we could substitute this F for centripetal force. So we can do FC equals MAC because we're trying to calculate centripetal force for acceleration now. So the formula for centripetal force is FC equals NV squared over R. I'm just gonna put, leave it like that. mv squared over r. And now we can replace this with nv squared over r, but I'm going to do r1 because it's asking for the centripetal acceleration in terms of r1. So r1 it is, equals mac. We can cross these two out because they can both be canceled out mathematically, and that'll leave you with your AC equals v squared over r1. Now we can replace the v with the tangential speed formula calculated from part D, 2 pi r1 over period. So we can just do that, 2 pi r1 over t, and that'll be squared. We're just replacing the formula right there. That's our ASC, by the way, v squared over r1, whatever, over r1 equals to AC. I'll put it here so we have more space for the later problems. Now we just need to simplify this even more by distributing the squares in here. So that will give AC equals to 4 pi r squared over t square of r. I just simplified this even more. I moved this r up, by the way. Now what can cancel out here? Your r's can cancel out, or the r squared and the r leaving just r. So to simplify that even more, so that will equal 4 pi r over t squared. That should be your AC in terms of r1. So now for part F, to determine the ratio, it's just a lot of numbers. We already found that for the AC, that is the expression. So it says AC of M1 over AC of M2. We just can plug this formula into each of these expressions here. So that'll be 4 pi squared r1, because this is in terms of M1, over t squared over 4 pi r in terms of r2 now, because M2 right here equals t squared. We can multiply this up, and to multiply this up we have to flip these two. So that will be 4 pi squared r1 over t squared times t squared. We're just flipping the bottom, 4 pi or 4 pi, sorry, I forgot to, I just noticed for part E, when distributing the square, you also distribute it to pi, so that's why these are squared. That's why this is squared. Yeah, that's my fault. So t for pi squared, hopefully you can read that. It's 4 pi squared r1 over t2 times t2 over 4 pi squared r2. So what can cancel out? The t2s can cancel out, the 4 pi can cancel out, the 4 pi squares can cancel out. So that will be leaving you with r1 over r2. That will be 0.4 meters over 0.75 meters. This is from the problem. R1 gives you 0.4, 0.75 meters are given from R2. So that relationship will give you, the meters would cancel out, leaving you with an answer of 0.53 for your ratio for the centripetal acceleration. Now for the ratio of your F of C, we are given the problem asks us to find the centripetal force or the relationship between M1 and M2. So we can plug in the centripetal force formula into both of these and then just number solve it. So we have M1 because we have what was it? We have M1 V1 because it's in terms of M1 is R1 over centripetal force for M2, which is M2 because in terms of M2, V2 because in terms of M2 again, and then over R2 because in terms of M2. I hope you see that. It's a 2. And then that will give, if we just plug in all the numbers that we found, so M according to the problem is 0.05 kilograms. Velocity according to what we solved in part D is 2.13, so 2.13 meters over seconds over R1 given in the problem is 0.4 meters over M2 in the problem 0.03 kilograms of velocity. I forgot to put a square here. Velocity according to the problem is 4 for M2 squared over R2, which is 0.75 meters. So if you calculate all of that, that should give you a value. All the units are canceled out because they're dividing being against each other, and it's also ratios. Usually ratios doesn't have units, and that'll give you 0.89. That's part G done. For part H, the magnitude of T1, so I'm gonna say C1 equals, I'm gonna make this true expression. Centripetal force equals tension 1 minus tension 2 because the centripetal force in the diagram has T1 and T2. There's two forces, but we see that T1 is greater because it's more pointing towards the center. It's inner, it's pointing more towards the center, and T2 is not according to also diagram A, right? T1 is pointing towards the center for M1. In terms of M1, T1 is pointing towards the center and T2 is not. So we're saying that T1 would be a greater tension for this problem here. So in terms of T2 for M2, I'm also going to say that T2 will equal your F of C, because in the diagram of M22, T2 is pointing towards the center. So we can say that that's a true expression right there. So we could say, if we simplify this even more, that T2 goes M2, because this is in terms of T2 over R squared. So now we can just plug and chug everything. According to what we found in part E, the centripetal force is equal to mv squared over R. So, or let me just rearrange this to solve for TO1. So TO1 should equal FC1. Yeah, TO1 FC1 plus T2. Okay, now T1, so F of C1 would equal you NV1, because this is turned to TO1, so it'll be mass 1 for this one that we're relating to for centripetal force for the first mass. And what we just found here for the T2, we could just plug it here. So now we just plug in all the numbers. Our mass given is 0.05 kilograms. Our velocity that we found in part C is, in part D is 2.13 meters per second squared. Our R1 given is 0.4 meters plus our mass for T2 will be 0.03 kilograms. Our velocity will be 4 seconds for V2, and according to the problem, it gives us 0.75 meters for our radius 2, and that should give you a value of 1.21 newtons. I pre-calculated this away too, and no direction because magnitude. So part I is pretty light work because we already found this expression already in part H. So I'm gonna put L here so we can save some space, because I know part L is gonna take up a lot of room. So part L, part I, we already see that T2, according to part H, that we found this expression 2v2 squared over R2, because according to this diagram, T2 is pointing towards the center, and it's the only tangent point towards the center. So we can say that FC equals T2. T2 is 0.03 kilograms, 4 meters per second squared, over 0.75 meters. So T2 would give you a value of 64 newtons pre-calculated, and no direction because magnitude. Okay. So for part J, I'll write it here, is asking us determine net force acting on M1. That's basically the same problem as part H. We know the net force will is just F of C1. And yeah, we can use the same expression that we found for FC1 because M1 has two tensions acting on it. So the net force is equal to T1 minus T2 according to the expression we found in part H. Net force is really just a centripetal force. So what we found, the net force acting on M1 is equal to T1, we found 1.21 newtons minus 0.64 newtons will give you a value of 0.57 newtons. And no direction again because magnitude. Part K, it's asking us what would happen to T1, T2 if the mass is increased. So I'm gonna say that it will increase, and I'll explain why for T1 and T2. So according to T1, we found this expression M1 V1 squared whatever, this expression right here. I'm gonna copy that again so that it's more easier to explain. So mathematically, just mathematically speaking, if we increase M2, we also increase M1 because it says that if the two blocks are massive and the speed and the R are the same, so these two right now in this scenario is constant. The only thing that's changing in these two are bigger. Mathematically speaking, T1 would be greater because the numerators are bigger, leading to a bigger answer here. So that's why T1 is greater, and we can use the same reasoning for T of 2. T of 2 equals, according to expression right there, M2V2 squared over R2. The numerator, if we increase the mass, these two are constant because these two ain't changing. According to this scenario, this context, numerator will be bigger because M2 will be bigger. So the answer, therefore, mathematically, T2 will be bigger, and that explains why if the system is replaced with the mass being bigger, the tensions will increase both for T1, T2. Okay, last one for part L. Before I record this problem took a long time, so I'll try to explain it the best I can. Part L, it says according to T2. What we found for T2 expression already, that we already found in the previous problems, is this right here. It's saying like what would happen if the times are changing, because we're given that table right there, right? So if the times are changing, the only thing that has time as a variable is velocity. These two are constant, these two ain't changing. So I can just use use V alone to help with find that table, because these two are constant. These two, in this scenario, this context, in the problem, since the time is changing, velocity is the only one that has time, because position over time. So time is changing, so we're just going to use V to indicate all this. So our V will equal position over time, and according to our position, that will equal 2 pi r, because circumference, but time is also changing. It's making a full loop. So I have to search this one, but according to arc tan, or the arc formula, whatever, since time is changing, it's going to make a full circle loop. That's why there's a 360 down there, whatever. So yeah, hopefully that explains it. No, that's just from arctan, because we have to use this because time is changing. So that's why it's going to make a full loop each time it's changing. So we can, from this formula right here, we can just plug in here 2 pi r 360 degrees over our time. And using this, it says also which quantities used to yield a straight line with the slope. The only thing changing in this tension again will be time. So the only thing that will affect time is the speed, aka velocity. So really, this is the vertical, horizontal. I'm thinking of this similar to like a VOT graph, basically, because the only thing that is changing is the time, and that affects velocity. So we can say with that knowledge, the vertical will be our position, and horizontal will be our change in time, because the only thing that's affecting is velocity. So that will be the slope, really, to calculate the magnitude of tension, because the only thing that's affecting is velocity, and it's like a VOT graph, and then yeah, whatever. Hopefully that made sense. So we can just set up our table from the problem. So it gives us 0.20 seconds, 0.42 seconds, 0.61 seconds, 0.81 seconds, and 0.99 seconds. Then our other two values that we can find is according to this problem, this expression that we just found. In order to find position, we need that degrees too, because time is changing according to the arc. So the two components we need to find is degrees, or our angle, and our position. We can use the angle here to find our position. Now, how we can find the angle is the expression that we already found here. V equals 2 pi r degrees over 360 L arc of tan over time, change of time. So we can just do 2 pi. Our radius is 0.75 meters according to the problem for V2. Pi over 360 degrees over our time. And our velocity in this case, aka V of 2, will be 4. V of t, let me just write this here. V V2 or V of t will be 4 because it's given in the problem, 4 meters over second. So we can write 4 meters over seconds. And now all we need to do is just isolate this, solve for degrees, and we have to do this 5 times because we are given 5 different times. So we just replace this with whatever time we want to solve. I'm too lazy, so before this I put everything on the Desmos to isolate and solve for. It shows x, but that's really for our degrees. So t at 0.20 seconds, our degrees will be 61.12, so 61.12 degrees. For t2, for this 0.47, 122.23 seconds, or degrees, whatever. 0.61 will be 186.40 degrees. 0.81 seconds will be 200. Okay, my video decided to cut off because I had no storage really remaining, but anyway, we're at 0.81, now we're 247.52, so 247.52 degrees. And lastly, at 0.99 seconds, it'll be 302.52, so 302.82 degrees. Now we got our degrees, we can solve for position. So already, position, we determined that it was 2 pi r of degrees over 160. We know our radius, according to T2, will be 0.75 meters. And now, since we found the angle for every single time, all we need to do, calculate the angle for every single one of the problems and solve for x. So I already did that on a calculator. For 0.20 seconds for 61.12 degrees, that gives 0.80. So we can write 0.80 meters positive because direction, and because it's positive, it's probably going to be moving to right, so that's why it's a plus sign right there. For 122 degrees will be 1.60. I'm just going to round it. 0.61 seconds, it'll be 186.40 degrees, 2.44, so 0.81 seconds, aka 247.52 degrees. It will be pretty close to a pi sign, 3.24, I think. I forgot what a pi number is. And for 0.99, that'll give you a value 3.96. I'll just round it. So that is part L. That's the whole table. That's all the information for the table, and we were given vertical. We determined it was position, and horizontal was time. And that, yeah, this would be the slope because time is the only thing changing. So that's basically just velocity. That's just the components for velocity, basically. Okay. Thank you for your time.